Hello everyone, this is Sir Aris. Today we will talk about Laplace, still Laplace transform, specifically the convolution integral. The con Consider this theorem if fs is equal to the Laplace transform of a function ft and gs the Laplace transform of the function gt both exist for s greater than a greater than or equal to 0, then hs, the product of fs times gs, can be written as Laplace transform of ht, where ht is given by this expression. The function ht is known as the convolution of f and g, and the integrals are called, these two integrals are called the convolution integrals. To prove this, um, what we need would be, so let's write fs as the Laplace transform of ft dt, and gs is the Laplace transform of gt. We will multiply these two, so to avoid confusion with the integration variables, let's change them. These are just indices that you can freely change. So let's say from 0 to infinity of e to the minus s instead of t. Let's use psi f psi d psi, and here instead of t we'll use tau s tau g tau d tau, and then we'll multiply the two. So hs, the product, is just fs times gs. That's equal to the product 0 uh, to infinity minus s psi f psi d psi, and then times integral 0 to infinity of e minus s tau g tau d tau. Okay, so if you just write the integral signs all the way to the right, that is fine. So minus s psi plus tau f psi g tau d psi d tau. We can also write, uh, let's say, if this integral corresponds to the tau, you can write g tau all the way here, d tau, which means that we are integrating first over psi. So e minus s, this contains psi f psi d psi. So we're basically just doing this operation first before integrating over tau. Now we can set, or you can change variables, t equal to psi plus tau, just so that we replace this. dt is d psi for fixed tau. Tau is fixed for this part, but it runs from 0 to infinity due to this, when we include this. Okay, so our hs becomes 0 to infinity of g tau d tau, integral from, so for psi 0, if this is 0, t is tau, so we start with tau. If psi is infinity, um, infinity plus whatever tau you have, that's also infinity. Okay, e minus t, f psi is t minus tau d um, t. Okay, now let's look at, before we do anything here, let's look at the region of integration. if we plot, basically we're looking at the values of t and tau. For our here, we t runs from some value tau, so this is t equals tau to t equals infinity. This is tau equals 0 to tau equals infinity. Okay, so we always start with this t equals tau, whatever tau is. So if we plot the line, this is a straight line corresponding to the equation t equals tau. Okay, so we always start with that line with whatever position here, and then we go to infinity. So say, suppose we pick this point here. When we integrate, we start from that all the way to infinity. So we can also start here to infinity. But that value runs from 0 to infinity. So the tau runs from 0 to infinity. So basically, if we pick an infinitesimal length here, which we call dt, it runs from whatever value of tau to infinity. So t runs from um, t equals tau to t equals infinity. Tau has a range, so it runs from tau equals 0, so 0 all the way to infinity. Okay, now if we switch, so switching the order of integration, we can do that. We may start for t, we start from 0 all the way, or for tau, we start from 0 all the way to this value of tau equals t. Okay, so we we do the integration of tau first, let it run from tau equals 0 to tau equals t, so this here. And for this case, t can run from t equals 0 here to t equals infinity. So we are basically taking this infinitesimal length here, the tau running from t equals 0 to t equals to this line. Okay, so if we switch the integration here, instead of doing this first and then this, we do tau first and then um, tau first and then t. So if we do tau first, this would be integral of um, uh, e to the minus, hold on, there's an s here. Okay, e to the minus st. Okay, dt. Okay, we do tau first. So this is for tau. It contains f t minus tau times g tau d tau. Now our limits of integration, tau runs from 0 to t, and t runs from 0 to infinity. So this one here, we can call this our h, or this is our h. So this becomes 0 to infinity of e minus st ht dt, which means that this is the Laplace transform of ht, and that proves the theorem. There are properties, so if we call ht as a product of f asterisk g. F and g are functions. Um, the formula would be um, this. Okay, there are properties. It follows commutativity law, distributive law, associative law. If you multiply with a function that's equal to 0 for all t, we get this. But if there's a function that gives 1 for all values of t, f times 1 is not necessarily equal to f. So for example, find the inverse of hs equals a over s squared over s squared plus a squared. So we write hs as a product. Hs is 1 over s squared times a over s squared plus a squared. Okay. This product, this can be our fs and this is our gs. So the Laplace transform or the inverse Laplace transform of fs is just the inverse Laplace transform of 1 over s squared, which is t. Let's call that ft. And the inverse Laplace transform of gs is so if you look at here, that is just sine of a t. Okay, let's call this gt. Now from our formula, the inverse of the product hs, the product of fs and gs, or inverse Laplace transform of hs is, from our theorem, is ht given by integral from 0 to t of ft minus tau g tau d tau. Okay, or substituting f of t minus tau, we replace t with t minus tau times sine of, here we replace t with tau. Okay, distributing, you have 0 t t sine a tau minus 0 t tau sine a tau. The first is easy. Um, it's simply negative t cosine a tau over a evaluated from 0 to t. Minus this one can be evaluated um, using what can we separation, or um, separation of variables. You have um, this would be tau. So if we set this as our u and this is our dv, then our u is tau, dv is negative cosine of a tau over a. Okay, evaluated from 0 to t. Okay, um, minus integral from 0 to t of d tau, or du is, that is simply d tau, and dv is um, or v is cosine, negative cosine a tau over a. There's this negative is actually distributed here. So this you can write minus t cosine of a t over a plus 0. We replace this with 0. That's um, t over a. The plus here is because it's the lower limit and there's a negative. Okay, this becomes tau or t. We distribute the negative sign, so this is plus um, tau or t cosine a t over a. And if you use the lower limit, this becomes 0, so the term becomes 0. Minus the integral of this is um, so negative because we're using here minus times minus is positive. There's a negative here. This becomes sine of a tau over a squared evaluated from 0 to t. These two here cancels. So you have t over a minus sine at over a squared minus which becomes plus 0. Okay. So our ht, the inverse, is simply at minus sine at over a squared. Okay. Another example, find the solution of the initial value problem um, y double prime plus 4y equals gt y 0 3 y prime 0 equals minus 1. So taking the Laplace transform, we have Laplace transform of y double prime plus Laplace transform for Laplace transform of y equals Laplace transform of g of t. Let's denote Laplace transform of y as y a function of s and Laplace transform of g as g capital letter G a function of s, and Laplace transform of y double prime is s squared ys minus s y 0 minus y prime 0. So we have s squared ys minus sy 0 minus y prime 0 plus 4 ys here here equals gs. So you can combine this and this, or you can substitute also. So if you combine those, s squared plus 4 ys, and we have this y sub 0, y of at 0 is 3. This is minus s times 3. Yeah, s times 3 minus y prime at 0 is minus 1 equals gs. So you move this to the other side, that becomes 3s minus 1, but we divide both sides by s squared plus 4. So you have s squared plus 4. Here you have s squared plus 4. Okay. Now um, div- we can distribute this denominator to these two terms. 3s over s squared plus 4 minus 1 over s squared plus 4 plus gs over s squared plus 4. You have 3s, um, factor out 3, and then we write this in a way that um, it would look like a familiar expression. So with 2 squared here, so the inverse Laplace transform is just cosine of 2t. So here we can also write as 1 half 2 over s squared plus 2 squared. 2 and 2 would cancel and go back here. Okay, in this one, we can write as 1 half of 2 over s squared um, plus 2 squared, the denominator, times gs. This is a product. This one we can call fs, which is the Laplace transform of ft. And in our case, ft would be equal to sine 2t. And gs is the Laplace transform of small letter g, t. Okay, now this becomes 3 cosine, or we take the inverse Laplace transform, giving us y, function of t. It's 3 cosine 2t minus 1 half sine of 2t plus 1 half integral of f of t minus tau g tau d tau from 0 to t. Okay, this finally gives us 3 cosine of 2t minus 1 half sine of 2t plus 1 half integral from 0 to t. We change here for our function ft, we change t with t minus tau. So you have sine of 2t minus tau times g. Let's say we call the inverse as, or the Laplace inverse transforms this capital letter G as small letter g, whatever that is. Let's have let's just take the argument t to tau, and that would be our um, final answer. Unless we are given the value of gs, we can get small letter g by taking the inverse, if possible.